So here we're given three vectors, u, v, and w, and we're asked to find a new vector, which is r, our resultant, and it comes from this vector sum here. So we need to express r in vector form and then also in magnitude direction form, and for the direction there, it needs to be measured counterclockwise from the positive x-axis. So how I'm going to start this out is I'm going to actually compute what r is based on just substituting in each of these expressions for u, v, and w. And that should be really easy because they're all expressed in component form, which are quite easy to add and subtract. So let's go ahead and do that. Remember that if you want to as well, you can swap them over rather than being expressed in the bracket form. You could equivalently write this as negative 1i plus 2j. But I'm just going to leave them in this kind of bracket form for now. So we know we have 2 of the u, which is negative 1 and 2 for the components. Then we need to take away a v, which is 6 and negative 1. And then we need to add on 3 of the w vector, which is 2, 2. So we can just expand these out like regular brackets. So 2 in here, and we need to do 2 times negative 1, which is negative 2, and also 2 times 2, which is 4. I'll leave this one. And for the last one, we've got 3 times 2, which is 6, and 3 times 2 again, which is 6. So we know that we now need to collapse it down so that all the x components go together and all the y components go together. So that means we got negative 2 for an x here, we've got minus 6, which would take us to negative 8, and then plus 6. Okay, so overall this is going to go to negative 2 for the x components. And then for the y ones, we're going to get 4. We've got a double negative here, so plus 1, and then plus 6. So overall, that's going to take us to 5 plus 6, which is 11. And again, if you're more comfortable, you can always rewrite it in this kind of notation where we would get negative 2i plus 11j. So this here answers the first part of the question where we wanted to get an answer for r in vector form. So either of these would be sufficient for expressing that vector in vector form. Remembering vector form just means that we have the horizontal and the vertical components listed separately. So now we'll move on to the second part, which is converting it into the magnitude and direction form. So for this, I'm going to draw myself a little diagram, which is going to help me out in terms of figuring out these properties. So what we've got here is negative 2 for the x component, which is telling us, remember that the Cartesian plane looks like this. So this is the positive x direction. That's where the little unit vector I points. All right, so if we have a negative, that means it's actually going the other way. So we've got a component of 2 going back to the left. And then here we have plus 11j. So plus is going to infer it's going up because that's the direction of our j unit vector, which aligns with the positive y, direction of the positive y-axis. So that means we're going to have, I probably should have made this a bit cleaner, but we're going to have 11 going up. So let me just move this down a little bit. So overall, okay, this is the total of the negative 2i plus 11j. It's our r vector, and the length of that side is going to be the magnitude, which is where we put the little bars in. And we know that this is always going to end up forming a right-angled triangle because the y and x axes are always 90 degrees to each other. So let's start out by getting the magnitude, which is that length of that longest side. So we can use Pythagoras' theorem for this. So we take each of our components and square them, so the 2 squared and the 11 squared, and then square root their sum. So this is going to be 4 plus 121, which is overall 125. So that's the length of this side, square root 125. So the other part, which is a little bit more tricky now, is getting out the direction of our vector. And it's telling us we need to specifically measure counterclockwise from the positive x-axis. So if I dot in here, this is the direction of the positive x-axis. So if I want to measure the angle of this vector, referenced from here, I'm going to need to go all the way around, okay, until I hit where that vector is sitting. So that's going to be the angle theta I'm looking for. Now it's going to be a little bit hard to get that straight away. So what I can do as a pre-step is solve for the angle in here. Okay, and that's within our triangle, so we can use our regular trig rules to get it out. And then once we've got it, we know that the number of degrees in a straight line is 180 degrees. So we can just take off alpha and we'll be left with whatever theta is equal to. So working on this triangle, I'm going to choose to use tan. And tan of alpha, okay, this angle here, it's equal to the opposite divided by the adjacent. So the opposite angle here is going to be 11. And the adjacent here is going to be 2. So in order to undo a tan, we do a tan inverse. And if you pop that into a calculator, it's 79.7 degrees. So we now need to do that bit where we convert it back to having theta. So we said that there's 180 degrees in a straight line, so that would take us all the way around to the other side here, but then we need to take off that bit for alpha and we'll be left with theta. So if we do 180 minus that 79.7 that we just worked out, we're going to get that our angle theta is 100.3 degrees. So the final step now is just to put it all together in terms of our magnitude and direction. So I can say that my vector, r, is equal to a magnitude of square root 125, acting at an angle of 100.3 degrees, and remembering that that's measured counterclockwise from the positive x-axis. So just to re-emphasize, this is our magnitude and direction form of that vector. So this expression here is equivalent to these vector ones up the top. So that's all there is in terms of this question.